Okay, good afternoon, dear students. In yesterday class, we discussed about the molecular measurement of osmotic pressure by Berkeley's and Motley's method. This is very important for 5 marks. In today's class, I am going to discuss about the laws of osmotic pressure or want of theory of dilute solution. Laws of osmotic pressure. Laws of osmotic pressure or want of theory of dilute solution or want of theory of dilute solution. Okay, here the want of are right here. The want HO yes. Want of theory of dilute solution or laws of osmotic pressure. Here it is the want of the from the measurement of osmotic pressure, the want of observed some laws. Here from some laws for dilute solution and which are also obeyed by gases and also obeyed by dilute solution. It is obeyed dilute solution as well as in gases. And here there are four laws are observed. The want of the first one is the Boyle's want of law. Boyle's want of law. Second one, Charles want of law. Second one is Charles want of Charles want of law. And third one, Avogadro's law. Avogadro's law. Avogadro's want of law. Avogadro's want of law. And last one is the want of law for dilute solution. Want of law for dilute solution. So this is the laws of osmotic pressure or a want of theory of dilute solution. According to this law, it is finding osmotic pressure. The want of observed these four laws. The given here, the want of law for dilute solution. The first law is Boyle's want of law. These four laws are observed. It is obeyed in a dilute solution as well as in gaseous. Here, first one is the Boyle's want of law, second one is Charles' want of law, third one is Avogadro's want of law, fourth one is want of law for dilute solution. Okay, these statements are very important for 1 mark question. State Boyle's want of law or state Charles' want of law or state Avogadro's want of law or want of law for dilute solution. Here is the first one, the Boyle's want of law. First one, Boyle's Wanders law, or it is also known as the first law for osmotic pressure, or first law of osmotic pressure. First law, osmotic pressure. Here, the first one is the Boyle's law, or it is also called as the first law of osmotic pressure. Here, the osmotic pressure is denoted by pi V. The osmotic pressure, this osmotic pressure is denoted the pi. Here, this osmotic pressure, according to this Boyle's law, the osmotic pressure of a solution is the osmotic pressure of a solution is inversely proportional to the volume of the solution containing 1 mole of a solute at constant temperature. Here, the statement of this, the Boyle's law, the osmotic pressure of a solution, the osmotic pressure of a solution, osmotic pressure is a pi, the osmotic pressure of a solution is inversely proportional to the volume of the solution containing 1 mole of a solute at constant temperature. This is a statement for Boyle's law. Or in other words, the osmotic pressure is directly proportional to the concentration at constant temperature. This is the second statement. Or it is you write first statement or second statement. I write here, in other words, the osmotic pressure is directly proportional to the concentration and at constant temperature. At constant temperature. In other words, the osmotic pressure is inversely proportional to the volume of the solution. The osmotic pressure of a solution is inversely proportional to the volume of the solution at constant temperature. At constant temperature. This is the expression. Pi is directly proportional to C at constant temperature. R pi is inversely proportional to the volume of the solution at constant temperature. And right here, this statement. The osmotic pressure the osmotic pressure of a solution is inversely proportional to the is inversely proportional to the is inversely proportional to the volume of the inversely proportional to the volume is indicated as V here. Volume of the solution containing 1 mole of solute containing 1 mole of a solute. 1 mole of a solute. In other words, in other words, the osmotic pressure, the osmotic pressure the osmotic pressure of a solution, the osmotic pressure of a solution is directly proportional to the is directly proportional to the is directly proportional to the concentration. 1 mole of a solid we write here at constant temperature. Here proportional concentration, here the concentration is indicated C at constant temperature. In your examination, you write this one or this one. The osmotic pressure of a solution is inversely proportional to the volume of the solution containing 1 mole of a solute at constant temperature. Or in other words, the osmotic pressure of a solution is directly proportional to the concentration C at constant temperature. Here I take it is pi V is equals to gas obey gases as well as dilute solution. Here pi is equals to a constant. Pi V is equals to constant. Pi V is equals to a constant at constant temperature. At constant temperature. At constant temperature, here the relationship is similar to the mathematical form of the Boyle's law for gases. This equation is here. This Boyle's law, it is similar to the mathematical form of Boyle's law for gases. Here, according to Boyle's one-Tufts law, the product of osmotic pressure here, the product of osmotic pressure and volume is constant at constant temperature. Here pi V, here the osmotic pressure and this volume is at a constant temperature. According to Boyle's law for gases. This is the Boyle's law or a first law of osmotic pressure. Next, second one, Charles' law. Then it is Charles one-Tufts law. I will write here only. Charles one-Tufts. Charles one-Tufts law. or this law is also called as second law of osmotic pressure. Second law of osmotic pressure. Here, Charles Quantock's law. In Boyle's-Quantock's law, the first one, the osmotic pressure is inversely proportional to the solution, the volume of the solution at constant temperature. Here, the Charles Quantock's law, the osmotic pressure of a solution at constant concentration. Here, at constant concentration is directly proportional to the temperature. Here, in Boyle's law, constant temperature. In Charles' law, constant concentration. It is the osmotic pressure is directly proportional to the temperature at constant concentration. On the absolute scale, here that is the pi is directly proportional to the temperature at constant concentration. Here the equation is pi is directly proportional to the temperature at constant concentration. See, this is a Charles Quantock's. Okay, this is for generalization is similarly mathematical form for Charles law for gases. This is a similar for Charles law for gases. It is a simultaneously effect of concentration and temperature on osmotic pressure. Okay, I will write here the statement of this Charles Quantock's. Charles Quantock's. Here, the osmotic pressure, the osmotic pressure, the osmotic pressure pi of a solution is directly proportional to the 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 at constant is directly proportional to the temperature on absolute scale. On absolute scale at constant concentration. At constant concentration C. Here the temperature is T. This is a Charles Quantock's law or second law of osmotic pressure. Boyle's law is the first law of osmotic pressure. Or this is a general equation or it is the general equation for dilute solution. For right here, the general equation for dilute solution, it combines the Boyle's law and Charles law. First law, it take a equation number 1 and second law, it take a equation number 2 combine to form a general equation for dilute solution. Here, this is a statement for Charles Quantock. Next, the general equation for dilute solution. general equation for dilute solution. General equation for dilute solution. Okay, here the general equation for dilute solution, to forming a general equation for dilute solution to combine first and second law. Here combining the first and second law of osmotic pressure for a solution containing 1 mole of a solute to obtain an expression. Here first one is the first law, pi is directly proportional to the concentration, or pi is inversely proportional to the volume, or pi is inversely proportional to the volume. This is a Boyle's quantities at constant temperature. Here also at constant temperature. This is a Boyle's quantities this equation taken from Boyle's quantities. Okay, second equation, take second law of Charles Quantities law. Second one is pi is directly proportional to the temperature. Here at constant concentration. Okay, this is a Charles law. Charles Quantities. Okay, this you take equation number 1 and this you take equation number 2. Combine these two equations, combining equation number 1 and 2. Here combining equation number 1 and 2. When we get pi, this is equation number 1, this is equation number 2. Here this is here temperature is here, and here this is a pi. Here finally you get pi is, and combine this equation, pi is directly proportional to the temperature, inversely proportional to the volume. See, pi is directly proportional to the temperature, inversely proportional to the volume. This is a combined equation. Equation 1 and 2 is combined equation, and form this equation when if both temperature and volume is varies. When if both temperature and volume is varying. Volume is varying. Here the pi v is equals to kT. This proportionality constant, the k is taken as proportionality constant. I am writing here it is equivalent here equal to pi v. This pi v equal to kT. K means it is a proportionality constant, where k is a constant. Here this equation I write here. This one, this pi v is equals to k into p, where k is constant. Where k is constant. This is a pi v is equals to k t here. The pi v is equals to k t. The want to obtain the value of K here. This K value, we want to find this value of K by substituting the value of K. Here they substituting the value of pi, this one pi value, the V value and T value. They substituting pi V T for sucrose. We discovered that for a solution of sucrose, the osmotic pressure is found here. The osmotic pressure is found to be here. The pi is a osmotic pressure of sucrose is pi is equals to 0.66. Here pi is equals to 0.66 and volume V is equals to 34.2 per liter. 34.2 per liter, and you know the temperature is 273 Kelvin. Here you know pi value of sucrose, you know volume and you know temperature. Substitute these three values in this equation here. I am substituting here the here Kp is equals to pi into V, where K is equals to pi V divided by T. Here K is equals to pi value 0.6 into V value 34.2 and divided by 270. Okay, the T value temperature 273 and this pi is 0.66 and into multiplied by 34.2. Finally, we get the K value 0.0821 liter atmosphere. Here the K value is K is equals to 0.0821 liter atmosphere. This is a K value. We want to observe this K value in sucrose. We taken a sucrose solution. Next, here, therefore, this is the value of K is a good agreement with the gas constant. This K value is good agreement with the gas constant. You know the gas constant is denoted as a R. Here the R K is replaced in this equation by V is equals to KT. Here the K is replaced for gas constant or the equation is pi V is equals to RT. This equation get pi V is equals to RT. Here this is replaced. This is a gas constant. It is agreement with the gas constant. This is a gas constant. Here we get pi V is equals to RT. And here K is a gas constant and pi V is equals to RT for 1 mole of a alkali solution. This equation is for 1 mole of alkali solution. For 1 mole of alkali solution. When you written pi V is equals to nRT, pi V is equals to nRT is the n number of moles of dilute solution. This is a 1 mole of alkali solution and if taken pi V is equals to nRT, n number of moles of dilute solution. Equation finally we get pi V is equals to nRT. This equation is known as the n number of moles of dilute solution. You taken n is equals to 1 here, n is equals to 1 will means here the n is equals to 1, then get this equation pi v is equals to rt. Pi v is equals to rt. For pi v is equals to rt, when you taken n is equals to 1, that is the n 1 mole of a dilute, 1 mole of a alkali solution or dilute solution here. 1 mole of this equation for 1 mole of alkali solution. That equation is the n number of moles of a dilute solution. This equation is called, finally, this equation pi v is equals to nRT is called general equation for dilute solution. This pi v nRT equation, this equation is a general equation for dilute solution. Next third law is the Avogadro's quantum. Okay, next third law, Avogadro's quantum law. Avogadro's quantum law. Okay, Avogadro's quantum law is stated at a given temperature, solutions are having equal molar concentration. Here, the two solutions, any of these two solutions having equal molar concentrations of different solute have the same osmotic pressure, same molar concentration, and different solute have the same osmotic pressure. This law is similar to Avogadro's law for gases. The statement for this Avogadro's quantum law, at a given temperature, solutions having, I write here, at a given temperature, solutions having equal molar concentration, concentrations of different solute, molar concentrations of different solute, have the same osmotic pressure. Have the same osmotic pressure. See, this is a statement for Avogadro's law, Avogadro's quantum law. Here, the all given temperature, solutions having any given temperature, all given temperatures, solutions having equal molar concentrations of different solute have the same osmotic pressure. This lies similar to the Avogadro's law for gases. This is our work statement for Avogadro's quantum law. This is only 1 mark in examination, only 1 mark question is asked. Next one, the want of theory of dilute solution. Laws of osmotic pressure. This is the laws of osmotic pressure. Finally, the want of theory of dilute solution. According to the want of theory of dilute solution, the osmotic pressure of a dilute solution is the osmotic pressure of a dilute. I write it again. Want of theory of dilute solution. Want of theory of dilute solution. Want of theory of dilute solution. Here, the want of theory of dilute solution, the osmotic pressure of dilute solution is the same as the pressure. The want of theory of dilute solution of osmotic pressure. Here, you take the laws of osmotic pressure. It is same as the normal pressure. Here, is the solute would exert if present as a gas at the same temperature occupying the same volume. Here, at a gas has the same temperature and occupying the same volume as that of the solution. That is, gas laws are applicable to dilute solution. This is known as Wonders law of dilute solution. This is the fourth law, Wonders law of dilute solution. Here you take when if a gas at the same temperature occupying the same volume as that of the solution, that is gas laws are applicable. The gas laws are applicable to dilute solution. These applicable to dilute solution or it is known as the Wonders law of dilute solution. Okay, next one. This is very important for 5 marks in 2018 question paper. Ask this question: the relation between the osmotic pressure of a solution, and molecular weight of a solute, or determination of molecular weight from osmotic pressure. This is very important. The relation between the osmotic pressure of a solution, and molecular weight of a solute, weight of a solute, molecular weight of a solute, or determination of molecular weight or determination of molecular weight molecular weight determination of molecular weight from osmotic pressure. From osmotic pressure. From osmotic pressure. This is very important for 5 marks question. Okay, here the determination of molecular weight from osmotic pressure. The osmotic pressure measurement have been used for determining the molecular mass of non-volatile and non-electrolytic solutes. Non-volatile, we are using the determination of osmotic pressure using non-volatile and non-electrolytic solutes. Here, a small amount of solute is dissolved in a suitable amount of solvent. Here, you taken a small amount of solute. The small amount of solute is dissolved in a suitable amount of solvent. Suitable amount of solvent so as to go. This is a sufficient dilute solution and its osmotic pressure is measured at a known pressure. Measured at a known temperature by suitable method. The substitution of various values in the equation, that is PV is equals to nRT. You know this equation, PV is equals to nRT. This is enable us to calculate the molecular weight. Here, this equation is enable to calculate the molecular weight. Here, you substitute the n value with here W by M. Substitute, therefore, substitute the n value is equals to W by M. Here, I write here PV is equals to nRT, therefore P is equals to nRT divided by, this comes here, division, P is equals to nRT divided by V. Here substitute n value, n is equals to W by M. Therefore, P is equals to, n means W by M, W RT divided by M into, here this is a equation. Okay, you are finding the molecular weight. The molecular weight, you rearrange this equation, this M comes here, M is equals to W RT divided by P into, this is a equation for finding the molecular weight. Here, where W is the weight of the solute and M is the molecular mass. Its molecular mass. W is the weight of the solute, where here, where W is the weight of the solute, weight of the solute, and M is the molecular mass, its molecular mass. M is its molecular mass. Okay, here the relation between osmotic pressure of a solution and molecular weight of a solute, or determination of molecular weight from osmotic pressure. You are finding the molecular weight of a solute. Here this is a M is equals to WRT divided by P into V. This is the equation. On this formula, you do problems. In next class, I will discuss this problem. On this formula, M is equals to W RT divided by P. Okay, I will stop here. Thank you.